So thanks a lot. I would say thank you for the invitation, but since you are one of the organizers, I feel that I am maybe a bit privileged. And so it's joint work, yes, with Johan Larsson, Quentin Klopfenstein, and Jonas Wallin. We just received the news 20 minutes ago that it was accepted at AIStat. So you'll see me happy instead of frowning and depressed about this work. And today we're going to talk the broad topic as a broad topic of the presentation is sparsity, for which we know since 1996 that we can perform jointly and in a convex fashion the tasks of regression and feature selection using the Lasso estimator. So the Lasso is defined as a solution of an optimization problem with a quadratic data fitting term and a non-differentiable convex L-One penalty. And using this convex L-One penalty, we have the key property that if our regularization strength lambda is not too small, then the number of non-zero entries in the solution will be very small. And this is due, we now know it, this is precisely due to the non-smoothness of the L1 norm around, not only at zero, but like all norms, but around the axis. So this object, this minimizer beta hat, statisticians love it. There are wealth of papers since the mid 2000s, and basically around the fact that you can prove that if your real model is sparse, if your data y comes from a real beta that is sparse, and you have nice enough properties on X, then you can recover your true sparse model. So that's very nice. And you can do it even in the setting where P is much larger than N. So you get not only recovery, but also very good error rates in terms of prediction. Now that is for the theoretical object. Okay, we know that it's nice, it's beta hat, but practitioners maybe would like to compute it, to use it in practice. And at first, when it was introduced, it was really a hard problem because of this non-smoothness of the L1 norm at zero. We had to resort to trig. We liked a lot smooth optimization, but non-smooth, we didn't know what to do. Subgradient descent is really slow. Gradient descent could not be applied. And then following, again, a wealth of works starting from, I would say, 2005, optimizers started to love this kind of problems too, because they noticed that they have a really specific structure. That is, you're trying to minimize the sum of two functions, in fact, usually denoted as f and g. And f is smooth. F is just the function that we see in ordinary least squares. And g is not smooth. It's making the problem hard. But you can compute the so-called proximity operator of this function g. In the case of the L1 norm, it's the soft thresholding. And so we started to call these problems smooth plus proximable. You have a smooth function and a function whose prox you know. And you can, in fact, use what the so-called splitting methods, in which you're going to try to minimize just f for a while, and then a step to minimize g, a step to minimize f, a step to minimize g. And this is the very popular proximal gradient descent algorithm, also called ISTA in the case of where g is the L1 norm. ISTA for iterative soft thresholding algorithm, that can even be improved from ISTA to FISTA, since the seminal paper of Beck and Teboul, where you combine this proximal gradient step with an inertial steps that gives you more and more speed as you progress towards optimum. And from this paper, it was now considered that solving, in fact, the Lasso was as easy almost as solving regular smooth optimization problem. Even more, we went from a change of mind from considering such problems from a curse of non-smoothness that prevents us from using classical algorithms, to blessing of non-smoothness. And I'm borrowing the expression from the very good review paper of Frank Hutzeler and Jerome Malik, because this non-smoothness is not imposed onto us. It's chosen by us. We choose to solve this problem. And it imposes a very particular structure on the solution, but also on the iterates. So you can improve you can build on the fact that the iterates are sparse, by using some additional optimization technique to make your optimization problem faster, using techniques that are called screening or working set, where basically you know that lots of coefficients in beta hat are going to be 0, and so you can try to discard them from the problem. So that's the big picture for the lasso. And even after, we realized that in the setting of machine learning, we can use even faster algorithms than proximal gradient descent, or even accelerated in its FISTA form. And the algorithm is called coordinate descent. And the idea of proximal coordinate descent is, instead of trying to minimize your function over t variable, the whole function at the same time with proximal gradient steps, you're going to perform proximal gradient steps in one dimension. So just you pick one coordinate and you do a proximal gradient step on this coordinate. It sounds both really simple and maybe too simple and naive. It should not converge. But if your function is smooth, it converges. And in the case where you have a smooth and separable function, it also converges. So on the picture here, you see the basic ideas of the two algorithms. First one is gradient descent. So here there is no prox, but the ideas would be exactly the same as there was a prox. On the left, you minimize with respect to the two variables. So your vector of iterates doesn't have a particular shape. Here, you are only allowed to update the first coordinate, the second, the first, the second. So you must move in lines that are orthogonal to the axis. And as it turns out, Lasso is the canonical problem that you can solve with coordinate descent. It's a smooth problem plus a non-smooth one, but that is separable. Okay, you can write the penalty as a sum of independent function over each coordinate. And here, each independent function is the same. And so the idea of minimizing over coordinates, because this part is smooth and in this part there is no interaction between coordinates, well, in the end, it converges, and it converges quite well. Here is an example from a paper of 2 years ago with Quentin Bertrand. This is gradient descent in blue, continuous line, and in orange, coordinate descent. Okay, so you see that it's much faster. In dotted blue, you have inertial GD, so just the Nesterov acceleration, and you see that CD, even if it's not accelerated, it's faster than algorithms such as FISTA in some cases. And the goal of our paper, it's just a small advertisement for what we did with Quentin Bertrand. We provided an acceleration of CD in dashed here that is exceptionally faster in some settings. What is the main reason for the success of coordinate descent? Why is it so strikingly good? Well, there are many. It's not completely understood, but the first one is it doesn't take too much computation power to compute the gradient with respect to one feature. To solve the one-dimensional problem, it's very cheap, and so you can update your full vector of beta in the same cost as you would do in gradient descent. Okay, that's not true in general, but in machine learning problems, computing the gradient with respect to one feature only is very cheap. For example, that would not hold true in deep learning anymore. You cannot do coordinate descent in deep learning, it's too complex. The second fact is that to have an algorithm that converge, you have requirement on the step sizes. Okay, if I go back here on the size of the step size of the steps that you can do here, and you are able probably to see it already on this picture. For coordinate descent, you are able to take steps that are way much larger, way larger, sorry, than the blue steps. Okay. So here, because of these step sizes, the 1 by Lj that you take in coordinate descent versus the global step 1 by L that you take in gradient descent, you are much faster. And this is a very fun experiment that we made with Quentin Bertrand. You take the CD algorithm, and basically the delta parameter here, it's just a scalar between 0 and 1. When it is 0, you take the step size of GED, and when it is 1, you take the step size of coordinate descent. That is much larger. And you see that when you use CD but with a step size that looks like the one that is equal to the one of gradient descent, well, basically the two curves are the same. Okay, so in a sense, it all boils down to the fact that with coordinate descent, you can take much larger step size. So you go towards the yellow curve, and then you converge much faster. Thanks to this coordinate descent implementations, we now have efficient solvers of the lasso, such as Celer, for example, and you can solve lasso problems with millions of variables in a few seconds on your own computer, okay, so without a cluster. And combined with the fact that many practitioners in applied science like interpretable models, so models where you can tell, okay, this feature is interesting and this feature does not enter the model, well, Lasso has found many large-scale applications in sciences such as biology, neuroscience, and geophysics. So I paint quite a pretty picture about the Lasso. It's good statistically, optimizers love it, and we have libraries to compute it super fast. But we are only at slide 7, so we are not done with the talk. There are still some issues. And Lasso is not a perfect estimator. It suffers from very well-known limitations that have been studied both by practitioners and theoreticians. The first one is its amplitude bias. Okay, because of this L1 norm, we penalize large coefficients too much, and so the coefficients are biased in amplitudes. We estimate coefficients that are smaller than their true value. Lasso is also not very good to deal with designs where you have sorry, I said correlated coefficients, it should be correlated variables. When you have two features that are really close to each other, Lasso does not really know what to do between them, and it will just select one, not at random, but almost at random, and without a very good reason. And most of all, we use Lasso a lot for variable selection. And in this task, it will find many false positives. Okay, so it will take into the model many variables that in fact should not be there. And you could say, okay, but that's because you don't regularize enough, your lambda parameter is too small. No, even for a very good, for a very large lambda parameter, you will get some false positives, okay? So there is one potential solution that is to use non-convex penalties. Okay, they will mitigate the amplitude bias, and it has been a research direction since roughly 2010 with penalties such as MCP or SCAD, for which we now have also efficient solvers. Also, second bit of advertisement for our solver SKGLM that we developed with Quentin Bertrand last year, that can solve MCP, SCAD, or LQ problem basically as fast as the Lasso. But when you go into this realm of non-convexity, well, you're never sure of the object that you get in the end. Okay, you lose the fact that critical points are global minimizers, and so you get an object. It may be good, it may be bad, but you don't know if it's the global minimizer and the one that is analyzed in theory. So today we'll not go off the convex path. We'll stay on the convex road. Please do not hesitate to interrupt me if you have questions. Okay, it will be more lively. And to improve on the Lasso, we're going to consider another penalty that is named the slope for sorted L1 penalized estimator. So as a disclaimer, I will use slope for the penalty and the estimator alternative. Okay, I know that the acronym is only for the estimator, but I will also call slope the sorted L1 norm. The sorted L1 norm is as follows. Instead of picking a single lambda, you take a sequence of p lambdas, because you have p variables, okay, by decreasing order, all of them positive. And the penalty is a weighted sum of lambda j times norm of beta j, but beta j reordered. Okay, so here's a parenthesis around the j is to say that we reorder beta by descending magnitude. Okay, so for the largest coefficient, you pay a price that is proportional to lambda 1. Then for the second largest, a price of lambda 2, etc. So largest coefficients are more penalized. It's a generalization of two very popular instances that you have heard of. Of course, the first one is the Lasso penalty. If you take all the lambda i's equal to a single lambda, you recover the Lasso penalty. But if you take just the first lambda non-zero and all of them zero, you end up with the L infinity penalty. Okay, you just pay a price lambda for the largest coefficient and then zero for the rest. As I solved it, the main advantage of slope is that it's convex. Okay, so surprisingly, I mean, or maybe not for you, it's convex because you can write it as a pointwise supremum of affine functions. And so affine functions are convex, it's still convex. And if you plot the level lines of slope in 2D for various values of lambda, here we take two sets of lambda i's, you see that you have kinks along the axis, like for the L1 norm, but you also have kinks when two variables are equal in magnitude. Okay, so along the orange lines, the unit ball of slope or the level lines of slope have kinks. Okay, and you see that as lambda 2 here becomes smaller, if lambda 2 becomes close to lambda 1, you get a diamond shape like the lasso, and if lambda 2 goes to 0, you get a square shape like the L infinity ball. So why is this object interesting? Well, I think it's interesting in itself, but the estimator itself, it's proved, it solves some of the problems that the lasso has. And the main one is that it has a much better false discovery rate control. So I was talking about the false positives that occur early on the lasso path, and they don't occur so early on the slope path. Okay, so this is much better. You don't end up with a model in which there are irrelevant features that were selected by the optimizer. A second nice property that comes maybe as a direct consequence of this many non-differentiable points on the slope unit ball is that if you use slope, it will cluster the coefficients. Okay, so if you're of course, it depends on the regularization strength, same as the sparsity for the lasso. But if you look at the solution of a slope problem, then you'll see that very often it takes a number in absolute value. It takes a number of distinct values that is much smaller than the total size P that it could take at more. And so we're going to use this notation quite a lot in the talk. We'll say that the values taken are C1 that is larger than C2 up to Cm, and it corresponds to a partition of the indices that is into sets C1, capital C1, capital C2 up to capital Cm. Okay. Now, if your real vector is also clusterized, then in a paper last year, it was proven that the sparsity pattern can be recovered and the order of the patterns can also be recovered. And let me emphasize, this comes really for free. You don't have to know the groups in advance. So it's not like a group lasso problem. Okay, you don't know C1 up to Cm in the solution. It estimates them for you. It also doesn't depend on the order of the indices. Okay, you have problems such as a fused lasso or TV in total variation in one dimension, where you will say, okay, variable 10 and variable 11 are likely to have a coefficient that is equal. Here, it's not the case. If you shuffle your coefficients, you'll get just the same solution affected by the same shuffling. And that is, in my opinion, slope's best property. This clustering coefficient, the fact that it achieves sparsity and clustering at the same time. So again, this is, as we saw for the lasso, all these properties are analyzed for the theoretical object. Okay, I give you an optimization problem. You suppose that you have the global minimizer, and then you can show that with high probability it satisfies this and that. But the optimizer that I am and the practitioner will tell you, okay, but now I want this object. I want to use it for my research. So how do I compute it? And it turned out, I said, surprisingly, in parentheses, for me it was a surprise at least, that if you look at this sorted L1 norm, well, you can compute also its proximity operator. Okay, and this, we like it a lot because it opens the realm of proximal splitting methods that is very rich and that have been developed in the last 2 decades. And if you're not aware of the prox of slope already, well, it's based on on a tool that is isotonic regression. Okay, so to compute the prox of slope at a value, you basically have to reorder the vector to solve an isotonic regression and then undo the sorting. And for those who don't know it, isotonic regression is in mathematical terms, it's a problem of projecting a vector onto the monotonic cone. Okay, so you have data here in blue, and you try to approximate it with a function that is non-decreasing. Okay, so the orange curve here, and you see that you have a few steps. And the link, the link with this and the fact that slope clusters coefficient is quite visible because you see that here values tend to be the same. Don't get me wrong, here you have then you have a shuffling to do, I mean an unsorting to do. So it does not impose that consecutive coefficients have the same values. Okay. And so if we can still use ISTA and FISTA because we can compute the prox, then maybe the problem is solved. We could still use proximal coordinate descent, and then we'll be able to solve problems with millions of variables. But unfortunately, it's not the case. And the main reason is that the penalty depends on the order of the vector, and so it's not separable as the L1 norm. Okay, so this at the same time beautiful and naive idea of minimizing with respect to only one coefficient, you cannot do it. And here is a very simple coefficient, a simple illustration in 2D. So it's a two-dimensional problem. The global minimizer is the orange curve, and suppose that you are here at a point where the two values are equal. Okay, so there is it's a point of non-differentiability. And you see that if you try to minimize with respect to beta 1, then you are already at the minima with respect to beta 1. And same if you turn your head and you look at what happens with respect to beta 2, you are also at a minima. So doing a proximal step with respect to beta 1 only or to beta 2 only will not make you move. CD cannot move along these lines, and thus it has to stay there. It's stuck. It does not converge to the global minima, that is the orange curve. But if we had an oracle here that gave us not the solution beta star, but the clusters of the solution, so from C1 to CM star, and the sign of beta star, okay? So it's a very generous oracle, still, because it gives us a lot of information. Then if we know this, the penalty becomes separable. Okay, so condition on this knowledge, the slope penalty is separable because you just have to find the value that is taken by beta star on each cluster, but you already know where it takes this value and which sign it has. Okay, so the data fit stays the same. Okay, it's just a different parameterization, but here the non-separable issue that we no longer have it. It's just a basic lasso problem now where we optimize over the value taken and with different weights, but the weights are fixed, and that would be our. We could plug in all the fast lasso solver based on coordinate descent that we have. So the idea that we propose, and that's why the name of the talk is coordinate descent for slope, is to try to alternate steps where we identify the clusters, and when we believe that we have identified the clusters, we take fast CD steps, okay? Or we take fast CD steps, and once in a while, you take a step to modify the clusters. So here is the coordinate descent algorithm. You move along axis, then you end up in a cluster, you update the value of the whole cluster, and then you're at a point of non-differentiability and you no longer move. Okay, so it's not good, it's a non-converging algorithm. Here you have proximal gradient descent. So it converges, you see that, but it takes very small steps. Okay, and even with line search here, it's a bit of a tricky example because you could think that if you did a line search, it would work better, but in large dimension, it's just a byproduct of 2 dimension here. Okay, in large dimension, it doesn't work. And here is the illustration of the approach that we use, where you have an hybrid. Sometimes you take a proximal gradient descent step, and the rest of the time you take coordinate descent steps. And because of this, you mix steps that are really large, like these ones, okay, and steps that allow you to escape the point where CD would be stuck. So here, you don't end up stuck like CD here, but PGD takes you out of this manifold, and then coordinate descent works again. Why do we rely on proximal gradient descent for cluster identification, and why can we rely on it? Well, we leverage the very powerful framework of partly smooth function. Okay, so a partly smooth function, I won't go into the details. It's quite a technical stuff, but it's smooth relative to a manifold. It's also called sometimes UV functions, because if you look at the function along the manifolds, it's like a U. Okay, it has to be smooth when you move along the manifold, and when you move orthogonal to the manifold, then it looks like a V. So it's sharp. Okay, and that is roughly what the three properties in the definition are saying. What we proved in the paper that the slope penalty is in fact partly smooth at any x, and the manifold, if you want the intuition, the manifold along which it is smooth is the set of all vectors with the same support, signs, and clusters as x. Okay, so it's a linear manifold. Actually, this result is an instance of a more powerful result by Samuel Vetter and co-authors. But here we provide a constructive proof that is interesting in C. Okay. And because now slope is partly smooth, we know from a result of Jingwei Liang that proximal gradient descent will identify the clusters in a finite number of iterations. So it's a generalization of a result that we know, for example, for the lasso. You know that for the lasso, if you do a big enough number of proximal gradient descent iterations, you will identify the support. Well, the same holds for the slope, but not just the support. You identify also the clusters. And now comes, so we can rely on 1/2 of our hybrid algorithm, because we know that it will, after enough iteration, take us to the good clusters. But comes the question of minimizing with respect to a single cluster. When we think that we have identified the cluster, how do we perform the coordinate descent step? Okay, and for that, I will introduce a few notations. This vector beta of z, it's basically, we are currently at the vector beta, and we will update the value of the cluster ck. Okay, so we say that outside of ck, beta z is equal to beta, it does not move. And it takes the value z in absolute value in on the indices that are in ck. Okay, so you move along your at your original vector plus z times +1 or -1 times unit vectors. And then minimizing this the objective in this direction, that is what we want to do with coordinate descent, it amounts to solving a one-dimensional problem. We only have to find the value z that is taken by beta on the cluster ck. Okay. So the data fit is not going to be a problem because the data fit is smooth. Okay, so we'll just take the gradients. And the thing is, how do we minimize this function h of z that we called the partial sorted L1 norm with respect to the case cluster? That is the value of the slope penalty on this vector beta of z. Okay, and beware, it may look like it's a simple penalty here, okay, because you have just the z times a sum and then another sum, but in fact this sum moves with z. Okay, here the sum of lambda j, it depends on z, so that's why write _z. It's because it's the permutation that reorders beta of z. In fact, it's the inverse of this permutation. Okay, so as z moves, the coefficient of absolute value of z also moves. And you'll see that in the following example. The partial sorted L1 norm has kinks. Okay, it's piecewise linear, but the more the largest the value z is with respect to the entries of beta that do not move, the more the slope increases. Okay, so we end up with minimization of a quadratic functional plus this penalty, but in larger dimension. Now, how do we solve the minimization for one cluster? Then we want to solve the problem with the partial sorted L1 norm, and we've seen that it was piecewise linear. Okay, so piecewise affine actually. since it's convex, it's sufficient to find a point where the derivative in the negative direction and the derivative in the positive direction are both positive, okay? And the derivative, so it's the sum of the derivative of the quadratic term, so a linear term, plus something that is constant by part, okay? Discontinuous and constant by part, that is the derivative of an affine function, of a piecewise affine function, okay? So what we provided in the paper is the value for this h prime, and you see that here the minimum is reached at 2, okay, because it's the only point for which both the derivatives are positive. Okay, both the left and right derivative are positive. So it's a bit notation heavy, but I'm just putting the slide for if you want to come back to it during questions. We provide first an expression for the directional derivative of this partially smooth of this partial slope. Okay, and it's a bit it's a bit heavy in notation, but it's valid. And then from this, by solving the equation, okay, by solving in Z the fact that g prime of Z must be positive. So if we go back here, by finding the only point for which the derivative is negative on the is positive both for delta equal 1 and +1 and -1. If we solve it, we end up with what we called the slope thresholding operator that will be the result of our one-dimensional minimization problem. Okay, so don't look at the values for which it breaks, but look at the size, the global look of the proximal operator. It looks like a soft thresholding operator, but soft thresholding would be equal to 0 there and then constant slope here. Whereas here you have many breakpoints that basically correspond to the fact that you're merging two clusters. Okay, so for this whole region, you are merging two clusters, and then that becomes so large that you escape the cluster, and then you end up in another cluster, etc. Okay, so we can minimize exactly our function with respect only to Z, and that will give us the full algorithm that alternates between proximal steps once in a while. Okay, so here it's a parameter of the algorithm. We take it equal to 5, and it's not super sensitive to what you take, basically, as long as you don't do these steps too often. I mean, you should do them from time to time because those are the ones that are guaranteed to give you the correct clusters. But if you do only them, then you never do the fast coordinate descent updates. So you end up with just PGD. And we find that a ratio of 5 was a good compromise between the two. When you don't do the proximal steps, you do a pass over all clusters. Okay, so you say, okay, I'm confident that PGD has given me the correct clusters. I will no longer touch the clusters. I can just merge them, but I will not split them. Okay, and I will take beta, pick a cluster, and update the value that is taken by beta on this cluster using the proximal operators that we just described. And the benchmarks were quite interesting. So our algorithm is in green, and there are many competitors, but one that may need a bit of the description is what we call Oracle CD in black dashed. Okay, so Oracle CD is you suppose that your Oracle has given you the clusters, and you are doing directly coordinate descent on the separable problem. Okay, so that's why it's an oracle, because it's a very fast algorithm, but it depends on the cluster that you don't know. So you cannot use it in practice. And you see that, well, this algorithm, because of its fast, large step size, it's really fast, especially for the 3 data sets that are large scale. Here, this one is a really small data set, and you can see that it takes something like 0.1 second to solve the problem. So it's hardly a large scale problems, but in cases where the data sets are big, CD would be nice. And you see that our green curve, especially when the regularization is high enough, our green curve is really, it almost approaches this curve. Okay, I think there's even a setup where we beat it, and that's a bit weird. I think that's an artifact of the experiment. Okay, so our competitor is systematically in amongst the best methods to solve the slope. And I'll be happy to take some questions about slope, but I will take the 10 minutes now to talk about the tools that we used for the practical experiments. And I'd like to introduce the BenchOpt project. Okay. So we have a website. BenchOpt is a library to make your benchmarks easier and more open, more transparent, more collaborative. We have a paper that was presented at NeurIPS in last December. And BenchOpt, the reason for BenchOpt to exist is that currently doing benchmarks of algorithms like the one I just presented, it's a pain. We need to do them because we often provide new methods, new algorithms to solve optimization problems, and we want to show that we are fast, okay? And we want to study in which setting we are fast or not. But it's painful to do this because you take your competitor methods and it does not work out of the box, okay? And I have an illustration of that. Here we have the ADMM, okay? So sometimes it works great. Here it's the best method, the blue curve. But here in this other setting, it's worse than just staying at zero, okay? Than just staying at zero. And it took us a lot of time to understand why, okay? So it does not work out of the box when you try to implement another method. Sometimes the code is not even available, so you need to recode it. And when you need to extend it to a new setting, so or maybe a new data set, maybe a new value of the regularization parameter lambda, a new choice of sequence for the regularizers of slopes, you cannot extend it easily. You put a new file, you save in a new results, you do a new plotting file, etc. The worst part is that we start all this from scratch for every project on which we work, okay? Say that tomorrow we want to work on another penalty, then we have to record all of this. And this is done by people in several labs at the same time. And every time there is a new PhD student that arrives, he or she goes through this painful path. With BenchOpt, we fix this problem by giving tools to build benchmarks that are open, reproducible, and extendable. How do we do it? Well, we structure the benchmarks into repositories. Okay, so they are on GitHub. They can be public or private if you want. If you're working on a secret method, you can do everything in a private repo. And we provide the BenchOpt Python package that is a Python command line interface that acts as a glue to run these benchmarks. The design of BenchOpt is to view an optimization problem as a combination of three key components: an objective, that is your type of function, a data set, so for example, X and Y, and a solver, for example, PGD and FISTA. And what BenchOpt is going to do is to take the combinations of all the objectives, data sets, and solver that you give, run the solver on this objective for the data set, save everything in a big CSV file, and then give you the tool either to produce a PDF for the figures or HTML reports where you can have interactive visualization of your results that you can even share online with your collaborators or with the readers of your paper. And the structure of a benchmark repository is dead simple. You have these three objects. So the objective is in a Python files. Each data set that has a common structure are in datasets file, in a datasets folder, and same for the solvers. So by design, it's modular and extendable. You have one reviewer that says, okay, I'd like you to test on this dataset, then you just add a dataset file and BenchOpt will work just the same. You want to track a new metric, okay, you have a reviewer that tells you, okay, you monitor convergence speed, but what about test loss? Then you add 2 lines in the objective file, and along with the objective value, you're going to get your test loss. This is what the HTML file looks like. Okay, so here it's a very big benchmark. It's a benchmark on residual neural networks. So as you know, there are many algorithms to train them. Here, I think that there are close to 200 competitors. Okay, and you can select the data set that you use, the objective, which metric you want to see. So here it's the training loss, but you could see the test loss, how you want to plot it, etc. Okay, so I know that for a very long time, I used to take when I was working on a project, I used to take snapshot of my computer with the 15 Matplotlib plots open, and I would send it to my co-author to say, okay, this is how our algorithm behaves. Now with Benchopt, I just send the HTML, and my co-author can just find all of the results and investigate by himself. The goal of Benchopt in the end is to make your life easy, okay, so that you can build on previous benchmarks. So we have existing benchmarks, something like 20 of them. And if you want to develop a new method to solve this optimization problem, then you just clone the benchmark and you get all the methods that are coded for you. You can use solver in Python, in R, in Julia, etc. You can run the benchmark in parallel, so it doesn't take forever to run it. And as we pointed out, I mean, Ali Raimi was asking a question on optimization. We pointed out to Benchopt, and he says, okay, it is what I wanted to do, but never took the time to code it. And it made us very happy because it's here to make your life easy and to make you do better benchmark while wasting less time. So we have a few existing benchmark. Of course, there's a slope benchmark, but many other of them. And if you want to start a new one with your optimization problem because it's not in there, then you can use the template benchmark and reach out to us if you need help. And for example, well, you see that it helps us to do better science. Okay, so here is an example on the residual neural networks, where basically you can say, okay, well, in this setting for this data set, then this solver is the best, and the performance varies like this if we change this parameter, etc. In terms of test error, in terms of sparsity of the iterates, in terms of training error, etc. And that's it for Benchopt and for Slope. I would be now very happy to take your questions.